taken from LDA calculations alongside the single site energies, where the Coulomb repulsion of the electrons has been taken into account. This is the wave function in Hamiltonian. It's not in P representation, it's in R representation, with the wave functions and their amplitudes. And there are this wave function in P representation. I'm sorry about that. Again, we see the plane, the copper dioxide plane. I will repeat that our study is two-dimensional. And on the right side, we see the wave function P representation. And actually, we can have an analytical result. This is, of course, has already been done and has been published. And at the bottom, we see the exchange Hamiltonian, which is in our representation. Well, now I would talk a little bit about the scenario. The scenario is a 4s electron with zero angular momentum, like kamikaze, falls to the nucleus and exchanges its place with the 3d electron, which is orbiting the nucleus. So they exchange their orbitals, and the Hamiltonian at the bottom shows exactly this exchange, and we are going to study this exchange to see what result we will get. On the picture, you can see the slight inset shows the R-dependent wave functions of both orbitals. This is the Hamiltonian for all bands, which transfers only to the valence bands we are interested in SD. We solve the characteristic equation and obtain values for A, B, and C, which are expressions for calculating S and D. Then I will just quickly move through the Bcs reduction. It is for theorists, this is quite well known, and if it's not, I don't have too much time to talk about it. Using Bogoliubov transformation, we represent our Hamiltonian as to this integral at the top, and obtain for the for the velocity, and this integral can be solved using simple mathematics methods, and we arrive at the expression for the order parameter, which is the theory of Valery Pokrovsky, published in 1961. I'll just show with this expression, which is the central one, and we'll continue. This is our energy bands of our calculation. We can see the P bands, which at the gamma points start from the EP, which are negative. The energy levels of the p orbitals are negative. The zero energy level is the energy level of the d orbital, and the band for the d orbital. Yeah, we see how it evolves through the momentums from the space, and the top is the completely empty 4s orbital of the copper atom. And similarly to the Bcs reduction, we perform a a reduction for the Landau Fermi liquids, where we approximate that the electrons as one electron goes from 3d to 4s, it does not change its momentum, and the other electron also. We have the destruction and creation Fermi operators, and the self-existent approximation is visible at the bottom, which is the average of their the averages. So next we perform a perturbative approximation of the electric fluctuations, studying fluctuations in the 2D density, and each the planes of the copper planes, if the resistivity in the z direction is too large, which we accept to be that case, can be viewed as a parallel plane capacitor, and we can use the Nyquist theorem for this relation between the averaged electric charge and the temperature. At the bottom, it is the approximate solution of the FPQ function, which we have introduced before. And from Yoffe-Millis, which stated that the imaginary part of the energy is proportional to the scattering rate, or which is 1 over the lifetime of the carriers. And approximating this is the dependence of the angle squared. And to solve this, after we have the Fermi liquid reduction, we we solve the Boltzmann kinetic equation for density fluctuations, having the ansatz of waves with amplitude nu p, and finally obtaining the result for nu as a function of the angles beta and theta. Beta is the angle along the wave vector of these small perturbations. So now we come to the results of our calculations. This is a plot for the dimensionless zero sound velocity and units of Fermi velocity, performed for a ferromagnetic sign of the exchange interaction. We know that it is the cuprum is QO2 is antiferromagnetic, but if there's a perovskite with ferromagnetic sign, we'll have this kind of anisotropy of the zero sound, with maxima along the directions and minima along the diagonals. And this contour deforms in the p/4 direction, which is symmetrically. And let me try to show this. Maybe it's not quite symmetrical, but okay. But the Fermi contour remains, its area remains constant, but we have ups and downs, and in this, for this angle, we have with this beta angle, we have electric charge and current oscillations equal to 0. And finally, this is the scattering rate which we have obtained. It doesn't matter the sign of exchange interaction because it is squared alongside the Fermi contour, and we see the hot and cold spots for our calculations. Again, like shown like the ARPES data. And if we remember, the ARPES data, the color it's almost the same. In 3 dimensions, the graphic look like this, with where we have shown the lifetimes of the carriers in cold and hot spots. And finally, let's see how theory and experiment come together. To the left side, we have both of them rescaled and one on top of each other. And to the right side, I don't know if this is seen, but they are stacked one after another to see the differences and similarities. So that's not so bad, and I finish here. Thank you.
Thank you.
Thank you.